And here we go.
There's the deluge. Here's ignition.
Doubling up.
Did it just do a Kerbal?
Back to the moon and beyond.
Put that in the big bag, you know.
Back at home, we all have a lot of work to do, but from here, it sure looks like a perfect world.
Propulsion continues to be normal.
We did have an observation.
Equination.
343 unfolds to go.
It's orange.
Water towers can fly!
Bingo! Right in the center. Where's Jacqueline? There it is!
That was surreal.
That's not what we want to see.
No!
Oh my God.
Yikes. You bet. Sure. We don't need any more of these.
All right, everyone. Hello, hello, hello. You know the drill. Let us know if you can see and hear me in the chat. Some 5x5s if you do. But welcome, everyone, to another Intrepid Museum Astro Live, where each month we talk to scientists and engineers who are doing some really amazing things in the space industry. We ask them your questions as well, and we're so excited to be having you on here. So I'm seeing yikes, you bet. Concurs, those are good. All right. My name's Alicia Siegel. I am the producer of public programs at the Intrepid Museum. There's the 5x5s, amazing. And I'll be your host today. As a reminder, of course, our show is live, so do feel free to drop any of your questions in the chat, and we'll be sure to get them answered for you. Also, as a reminder, Astro Live is supported graciously through a NASA cooperative agreement awarded to the New York Space Grant Consortium. So we thank them, as always, for their support for our show as well. And of course, for all of you all for being here too. So we're so excited to be kicking off yet another season of Astro Live. What an amazing year we had last year. We are so excited to be diving full force again this year. We're going to be exploring one of the most ambitious and inspiring, I think, scientific missions to date, which is the James Webb Space Telescope. So since it was launched back in December of 2021, it has really allowed us to look farther into the universe and also further back in time, if you know how that works, than ever before, showing us some of the earliest galaxies that formed after the Big Bang, showing us some really incredible views of stellar nurseries where stars are born, and also giving us insights into things like atmospheres of distant worlds that are orbiting other stars. Who knew all of the things that would be unlocking for us? So this is a really exciting topic. Getting Webb up, of course, was also a bit of an engineering challenge. Some of the earliest of our viewers here, you all might recall that we actually did another Astro Live program back in 2020. I looked that up, it was a while ago, talking about this challenge, actually comparing it to origami and how they had to fold everything. It was designed to launch folded up in the rocket and then unfold itself in space through a very complex series of deployments. It was a really, really innovative challenge, and so much of that ingenuity has really paid off. And so today we are going to be exploring both sides of Webb's story. Back then, it hadn't even launched yet. So now we are seeing the benefits, all of it. We're looking at the remarkable efforts of the building, the testing, the launch, the commissioning, and as well as some of the ongoing discoveries. So enough of me blabbering on here. I am so excited to be welcoming to our show today someone who, again, if you watched our previous one back in 2020, you might recognize her, Begonia Vila. She was actually on our show, as well as Nicole Colon. They are two key members of the Webb Space Telescope team. So Dr. Begonia Vila is Webb Systems lead at NASA's Goddard Space Flight Center. She played a major role in Webb's development, the testing, again, the launch and the commissioning. And she serves as systems lead for two of Webb's instruments, including the Fine Guidance Sensor, and continues to support the Webb operations while also working on NASA's upcoming Nancy Grace Roman Space Telescope. And joining her is Dr. Nicole Colon. She's Webb's operations project scientist, and she helps to oversee the scientific operations of the observatory. She's an astrophysicist and exoplanet researcher, and she's also held leadership roles on major missions, including Hubble and TESS, and she studies the atmospheres and the evolutions of planets beyond our solar system. So we have a really exciting range of things that we can talk about today, both in the creation and the deployment, as well as some of the scientific discoveries that we've had ever since it's launched. So both of you, welcome. Thank you so much for being on our show today. We're so excited to be championing this amazing project, the James Webb Space Telescope. And, for many people out there watching today, Webb has become this household name. But for those of us who are joining that may not also be following astronomy closely, what would you say actually makes the James Webb Space Telescope different from every space telescope that has come before it? What's so special about it?
Do
you want to start off?
Sure. I think partly is what you are saying, right? Is the biggest telescope we have launched into space to date. And the fact of having those gold deployable mirrors, and that huge sun shield, right, as big as a tennis court. So definitely that drives this special time machine. But I also think it's the discoveries it's doing, right? It's doing everything we were hoping for and even more, and is uncovering all these early images of the universe and this way of evolving that we didn't know about before, right? And is helping to rewrite science. So I think everybody's excited, like we all are, with all these things unfolding right now that it's in operations. Nicole,
what about you? What do you think?
Yeah, I will definitely add, I joined the project in 2019, so just a couple years before it launched, actually. So I missed a lot of the early, development and all that, but it was very humbling to be able to join such, what you knew was going to be such a powerful telescope. And in fact, it has been, the most powerful telescope NASA has ever launched, but it's also exceeded our expectations on so many levels. And so we're just really pushing, the boundaries on every scientific facet. And, astronomers out there are using the observatory to do things that we probably didn't even think were possible, before launch. So yeah, just to add to what Begonia said, it's been an incredible journey. I can't believe we're almost at 4 years of science with this observatory already.
It's amazing. And truly, I think obviously when Webb was first being developed and the first news broke that, oh, this thing's going up and everyone, sees the cool, of course, I've got my earrings on to match, right? The cool pattern of like the mirrors and everything. But I think the thing that really resonates the most with people is seeing these images that Webb has sent back, right? Like I am guilty as charged. I absolutely had them as my computer background screen and my phone background screen. Behind you, Begonia, of course, you've got, an image as well. They are just gorgeous. They are so beautiful. What do you wish that people really understood that they're looking at, though, when you see those pictures? They're beautiful. They're rainbow colors. Is that what they really look like in real life? Or like, is there something that people should know and understand about these pictures?
Yeah, actually, so I have an example. If we pull up the Pillars of Creation image that I've shared, it shows us what the images actually come down as. So they come down as like this black and white, raw data file, essentially. But it's just like, I don't want to say it's just like taking a picture with your phone, because obviously the observatory has these 4 instruments that are designed to be extremely powerful. But what happens is that we have to take the raw data and then it essentially gets processed, and we use different filters, different wavelengths of light, and we combine the different images to get something like the beautiful Pillars of Creation on the right, which is this giant region of where stars are forming and eventually planets could form. But it's a process to get there, even with a telescope as powerful as Webb, just because we have to do some of it in phases, taking images in different filters, stacking them, pulling out the information that's buried there. We just have to get to it.
It's amazing how all the different layers and like really the teamwork, I guess, that goes into all of this. There's so many different elements to get to those beautiful images, and it's really surprising. I remember being very surprised as well, being like, "Wait, you're getting it in like black and white? How is that possible?" But all the different layers, it's just absolutely stunning. All right, so let's talk about just the process of everything from the concept to the cosmos, right? That's what we've been calling this particular show. So Webb took decades to develop, right? So what, I guess, Begonia, this is kind of leaning into your wheelhouse now with the start of it. What problems were scientists and engineers trying to solve, like that existing telescopes couldn't already do? Why did we need James Webb in the first place?
Yes, James Webb is one of these that we call decadal survey telescopes, right? Every 10 years, the scientists, for example, in the field of astrophysics, get together and they ask things like that, what things we will want to have answered next. And they propose to NASA normally 4 missions, and NASA chooses one of them. And these missions are the wish list, but of course, they need to become a reality, and all of them require new developments, right? We have technologies, we don't know how to do them yet. We understand what needs to be done. So that's why these missions take always a little bit longer to do them, test them, and make sure we are there. So in this case, yes, this telescope, the idea was to look back in time, right? Take images of the first galaxies and stars that form in the universe and see how they evolved to eventually become a galaxy and where we are, right? And that required looking back in time. So that immediately drives the wavelength, which is that infrared, right? The light from these faraway objects has been traveling for billions and billions of years in a universe that's expanding. So that means that light is going to stretch, the wavelength stretches, that means it goes to the infrared. So clearly we needed to look on the infrared, but that introduces challenges in itself because the infrared, we can think about it as heat a little bit, everything emits heat. So we need to cool down everything and we need to get really cold, right? Webb is operating pretty close to absolute zero, 40 Kelvin for the instruments. One of them can go even colder to 6 Kelvin. So that means we need to cool it down, right? And that's where the concept of that big sun shield came up, right? To give it shade so it could detect these faint signals. And then you have the other part, which is we want to collect as much light as possible because some of the signals are going to be very faint. So that drives the size of the mirror, right? A bigger mirror, we collect more light. But as you mentioned at the beginning, we need to fit all of this inside the rocket. So that drove the need of having something that could be folded and we could open it in space. And this is just without touching what of the 4 instruments and the guider, the 5th component, are carrying, right? Which maybe we'll talk a little bit more, and Nicole, I'm sure, will, as it shows the science, right? These key instruments to be able to take images, to take spectra, to be able to look to planets, the atmosphere, see if those planets have an atmosphere, and to also, there was a request, can we also look on our own solar system, which is a different way of operating a telescope, right? So all of that folded, many iterations to come up with something that could be done, technologies to be developed, and that could be tested and launched and operated. So, yeah.
Yeah, and you mentioned that primary mirror. I mean, it's so big. It's larger than a school bus, they say, right? So to have to fit something like that inside of a rocket fairing, what were some of the engineering challenges that kept you guys awake at night trying to do that?
Yes, I mean, it's a big mirror. The idea was to make it of 18 smaller mirrors. They are made of a special material, which is beryllium. That drives something behind the scenes, which is you are going to be cooling down to very cold temperatures. And we know the materials change when you cool them down and things move as well. I always say it's like when you put something in the freezer, right? But we cannot build it or at those temperatures, right? So we build it at normal temperatures, and there is a big team that models how things are going to change when they cool down, and we place them together at ambient, knowing how they are going to change. And the mirrors at the beginning were really heavy. They are made, they get hollowed out, right, to make them lighter. And then we know there are 18 smaller mirrors that once we are on orbit, we need to align. That mirror on orbit has to behave as if it was a single mirror. You can see there one of the super cool images, right, when the mirrors are being assembled. To assemble them, we were looking up, which which is kind of the worst thing you can do, because any material, though we are on a clean room, we are keeping this as clean as we can, but any material is going to fall from the top down, right? And you see, as it was being assembled, the mirrors had these protective covers, and you see there are two of the engineers. Now that they are assembled, we are removing those covers, and those mirrors have some mechanisms in the back that will allow us to align them once we are on orbit, which is another process that had to be developed, and maybe we'll talk a little bit about that. And they are covered in gold, right? I always say the mirrors, our eyes look invisible, like Hubble, and our mirrors at home are covered in aluminum, silver, which is something that reflects visible light really well. If our eyes were infrared like Webb, all our mirrors at home will be gold, right? Which is a material that reflects that infrared light very well, which is what we needed for Webb.
So that's why you chose the gold then, I guess.
Exactly. Yeah,
Infrared.
it's a very good material that reflects the wavelength that we were going to look at. Yes.
Sure. Okay. So as you were just saying, it had to unfold itself in space. It had all of these like single point failures opportunities, right? So how nerve-wracking was that design philosophy? I know you said you tested it a ton in the different temperatures and everything like that as well. I mean, that's we have an animation here that kind of shows this as well.
Yeah, this is, you see how complex it's been there. Of course, the first thing we were deploying within half an hour of the launch is that solar panel. Everything we launch into space has some power in a battery, but we are going to get the energy from the sun. So we needed that solar panel to deploy. And I think if you see the launch of the video, you can see that panel opening up about the 30 minutes after the launch. And then you can see that obviously the antenna to be able to communicate. And then another super cool thing, which was that sun shield, as big as a tennis court. You can see it was folded inside a protective layer. And we were going to fold it down and then start stretching each of those wings. They are made of another special material, Kapton, and you are going to see there is like 5 layers. And that's kind of like a beach umbrella. That sun shield is always facing the sun and the earth and the moon. So the mirrors and the instruments, which are mounted on the back of the mirrors, that black structure that you see is where the instruments are, that is always facing the other way. And that's how passively we can get as cold as we need to for operations. And then you saw as well how we are deploying that secondary mirror. So the light comes on the big set of mirrors, bounces back to that secondary mirror that you see there, and then it goes in through the black hole that you see in the center, which is where the third mirror is. And then you have the instrument. Each of the instruments has its own set of mirrors to be able to capture the light and take it to the cameras that each of the instruments has. So it was, as you say, very, very nerve-wracking, 157 single point failures, which is something you never want to have when you launch, because as the name indicates, if any of them fails, it could be the loss of the mission. And you can see there, you see, I was lucky to be part of the broadcast for the launch in Spanish, and we didn't know if we could talk about the solar array being deployed in case, it didn't happen or it was delayed. And I think we were all excited real time because we could see it. So we are like, oh, yes, there it is deploying. And now we are going to have power, and then we'll be able to continue with the mission. So the deployments took about 30 days to fully complete. And it was exciting every day. We were there, exciting for today. Everything went well. We are coming back tomorrow. We're hoping the next thing goes well, day after day after day, until we were sure everything was ready. And we knew it was ready because we get the telemetry down and we could see that the instruments were cooling down and the mirrors as well. So we knew, things were going really well there. And you can see there the Mission Control Center, our mission operations manager at the time, Carl, and we are all in different consoles. You cannot see them, but we are there 24/7 for 6 months to accomplish what we needed to do to get it working as it needed to be. So exciting.
Yeah, I mean, I remember watching that. What an exciting and unifying time for collective effervescence, right? That's what we've been saying about like the Knicks, here in New York and everything too. It was such an exciting time during the pandemic. We're all, stuck at home. It's 2021, and like for the space community anyway, the space geeks to all be tuning in and like seeing this launch and being like, oh my gosh, we're doing it. This is crazy. This is amazing. How amazing was that? My goodness. So yeah, many people remember that launch, but as you were saying, like the real suspense kind of came after that. Watching it go through that deployment sequence and knowing, I guess on your end, like we didn't realize it, but at that time that there's no way to repair it if something went wrong. It's not like, Hubble had the servicing mission to, fix the mirror, but like what happens? Like if something didn't go wrong, it's just instant mission failure. That's it, all that for nothing.
Well, yeah, we were very far away, right? We are 1 million miles away, 4 times the distance of the moon. So we knew we couldn't go there to repair it. We rehearsed before we launched all the activities we are going to do for those 6 months, minute by minute. We know, how long something is supposed to last, what responses we need to get back to show that everything is working. And we have contingencies, right? Like things that we could do. Some of them were easier than others. For example, if the sun shield wouldn't deploy, we had different contingencies to try to rotate the telescope to get it to undo. But we knew if we were going down that path, it wasn't like a good day. Luckily, we didn't have to do any of that. We knew when we had the sun shield open and you saw the mirrors, the wings of the mirrors open up and the secondary mirror, even if the wings didn't open, we knew we had a mission and we wouldn't have all the light, but we knew ways to do that. As soon as we knew all the mirrors were deployed and we had to start the next phase. So the next phase that took about 2 months was to align those mirrors. So when everything is cold enough, we choose, a star was chosen to be able to align those mirrors. And the first time we take an image with that star, we are going to get 18 stars down to the ground, right? Each of the mirrors behaves as a single mirror. So that's the next phase. We are going to get these 18 stars in different parts, and we move each of the mirrors to see which star moves. So then we know that the star is the image of that mirror. And we can then start moving those 18 stars and put them in the shape of the mirrors. And the next thing we are going to do is they are all out of focus, right? Each of the mirrors is slightly out of focus. So there is a whole process of aligning all of those 18 mirrors to eventually make a single. You wouldn't know that it's not a single mirror. And you're seeing there the image of a star that was famous, but famous just because it allowed Webb to be aligned. And you can see there the final image where we see those spikes. Those are an effect of having those 18 segments there with what we call the struts to hold them together. And you can see this first image, which we couldn't share until it was allowed to be shared, but we were seeing them real time. And all those fuzzy things you see behind are galaxies. Even on that image, we had about 250 galaxies that I hadn't seen before. We kept saying, any image we take is being photobombed by galaxies in the background. So during those 6 months, and then we knew already how amazing this telescope was going to be. And that was after aligning the mirrors, we started the process of taking images with each of the instruments to be able to calibrate them and make sure everything was working well. And we were taking the precursors of those first science images, and it was amazing. I tell you, in the room there, we already knew this telescope was exceeding all our expectations. You are seeing there the little pieces of the sky that each of the instruments that Webb has are able to see. We have one of the instruments, which is a camera, the NIRCam, the near infrared camera. That's the contribution from the United States, the University of Arizona. It has four little squares of the sky that it can see. 2 little squares that you can see there, the near spec. That's a contribution from Europe, from the European Space Agency. And it's this instrument that is able to take up to 100 spectra of objects at the same time. And then we see the MIRI instrument, another contribution from Europe that allows us to go even further into the infrared. It lets us go to 25 microns because it carries its own cooler on board. It gets it down to 6 Kelvin, almost absolute zero. And then you see the two contributions from the Canadian European Space Agency, which are the ones I look after more. One of them is the NIRIS instrument that has different modes, and it lets us find planets that are closer to the stars more than the other instruments. That's one of the modes it can do. And then, of course, the guiding instrument, right? It allows us to grab a star, keep the observatory pointed, and keep it really stable. We send the information of that star 16 times every second, so the science can be taken without the images and the spectra being blurred. And this was the image to show that the main mirror was aligned, so all the instruments had everything in focus, and then they were optimized for the science, right?
The images are just so stunning. And it's funny, at the museum, prior to Webb anyway, when we would show, pictures of like the Hubble, the deep field, like that huge image of everything. We always say they pointed at like this tiniest little spot of the sky, but it showed us all these galaxies and everything. And everyone's like, oh, it's a bunch of stars. And we're like, actually, no, like that's all planets, that's all galaxies, right? But galaxies, planets within the galaxies. So would you say that a good rule of thumb when looking at these pictures then is that the star is the thing that has like the burst coming out of it, and then all the other dots are the galaxies essentially?
Correct. That's totally correct. The stars are so small that they cause that diffraction pattern. Yeah. And you are totally right. Everything else is galaxies or clusters of galaxies or interstellar gas or anything else that we are observing. Yes.
That's usually how we would point it out. So there you go. Fun from party trick for all of you at home. Yes. If you see an image, you can go, actually, look at count how many stars are in there. And it's just the ones with the burst on it. So we just looked at that picture of the fine guidance sensor, those images. That's one of the ones you worked on, right?
Yes, that's the one we work. And of course, the observatory, we have a catalog, right, of stars that keeps being improved. But you can think of, we are looking all over the universe. Webb can look all over the time if in a given year it's able to observe any part of the universe. And you can think there are parts of the universe where there are lots, they are very crowded, lots of stars, so we need to operate there. Parts of the universe where we hardly have any stars. And then we have to be able to work, if you're looking at a galaxy, I'm sure we'll see some of the images, there is maybe dust or there is an arm, and it presents different challenges for us to be able to find the right star in there. And we mentioned briefly, Webb is special, not only able to show us those older objects, those primordial objects, find planets, check if those planets have an atmosphere or their temperature, but it can also look on our solar system, going beyond Mars and over. And that for us is a different way of observing, right? When we are looking something that's very far away, those stars are fixed. We are just keeping them in a single position, so the science is fixed. When you think about looking something on our solar system, they are near us, so they are going to move. It's the same as if you're looking at Mars over the night sky, if you're looking at it overnight, it's going to be moving, right? Any of the planets on our solar system are going to move. So the guiding instrument has to operate differently. It has to keep that object stationary for the instrument that wants to look at it. So we do that by moving the star. We choose a star and we know how the science target is moving on the night sky, and we move that star. Basically, we move the observatory in the path and at the same rate that the target we want to look at is moving. So for the science, the effect is that their target is stationary, right? So that's something that you said there is a big thing behind to get the operations, right? To schedule the visits and to know what we need to do to get the science that happens seamlessly in the background to be able to get the images and bring them down to here, to the Earth.
Absolutely. And I want to bring you, Nicole, in as well. Speaking of the science now as well, we got it built, we got it launched. Obviously, I'm sure the science teams had, some input into like the things you wanted to work on. So in the design element and everything. But I would imagine that precision is also really important, like scientifically. Can you talk a little bit about like why it's so much better to have that precision and how it's able to precisely point like that?
Yeah, well, one thing I want to set the stage for, is a lot of the original science goals of the observatory, they were set 20 plus years ago. So, I study exoplanets, distant planets around other stars, but when Webb was in early design phase, we hardly knew of any exoplanets out there. And now we know of over 6,000. So, like, that's how quickly some of the field evolves, right? And so the observatory, like some of the instruments were designed to, along the way, to complement the science as it evolved. But at some point, you got to, just finish the instrument and then get it on the observatory, right? So you can only design so much. But when you have a capability like this fine guidance sensor, that's able to point so accurately and stably, there are some times where we're taking science observations that, are hours long and sometimes over a day long. We'll want to stare at one object. And so imagine, you trying to focus on one object for 24 hours without blinking. That's not something we can do, right? As humans. But the observatory, yeah, having just this exquisitely operating guidance system really helps us push and keep the instrument stable, the observatory stable. So, imagine again, you're taking a video with your phone, and your hand is shaking, so you put it on a tripod so it's a little more stable. It's kind of like that concept, right? You want as much stability as possible so you're not shaking around. And that really helps us understand every photon that we're collecting from these distant stars, these distant, galaxies, out to, not long after the Big Bang. So it's just an incredible way that the observatory is able to come together, for so many different science cases, having not just the guidance system, but as the other diagram showed, the four different instruments that are really operating in tandem to just explore at all these infrared wavelengths that we otherwise didn't have access to before.
And it's not just your team, right? Like I was reading that people, I don't know, people, research institutions, I suppose, can like request time on the Webb telescope and like can do their own research. Do you all have like a hand in that as well? Or do you just sort of like, all right, you can log in from X time to X time and do whatever research, don't break anything, and then you come back? Or do you do it for them and give it to them?
Oh, yeah, this is a great question, because there are many ways that people can use Webb and collect data. And so, firstly, I will say now that we're almost 4 years into operations, there's a whole bunch of data that's public on an archive. So it's the Mikulski Archive for Space Telescopes, or MAST. And so that exists to host the JWST data, all the data that's taken. Some of it does have what we call an exclusive access period, maybe for up to a year. But after that point, anyone can go from around the world to download the data and look at it, look at the images, look at, the spectra, look at all the facets, look at even some of the engineering data behind it, that was collected at the same time. But that's, once the data is taken and it gets put in this online archive, essentially. But how we get to the data in the first place, there are literally thousands of astronomers around the world who propose each year to ask, what science could we do with JWST? What science questions do we want to try to answer? And it ranges from everything, as Begonia mentioned, from studying Mars in our solar system, to comets, out to the earliest forming black holes, and everything in between. And so literally thousands of astronomers are proposing each year. We actually get requests for so much observing time. We basically get like 12 years of ideas in each year. So we cannot do all of those in 1 year, right?
How do you prioritize that then? Is it first come, first serve, or do you have to weigh it out?
I know it's what we call very oversubscribed, but like very popular. And so yeah, these astronomers come together and they put in all these amazing ideas. But yeah, there are literally only so many hours in the year that we can observe, right? And so what it boils down to is we have this incredibly powerful what's called a peer review process. So we have thousands of astronomers submitting ideas, but then we have another hundreds of astronomers coming together to review all those ideas, and then they review, rank, recommend ideas, and then it's actually the Space Telescope Science Institute in Baltimore that we work closely with. They oversee and run all the core science operations and this review process. And so they will come out and say, okay, out of these, 12 years of ideas, these are like the 1 year that's recommended for this year. And the rest, we'll have to try again next year, essentially. And
do they, I guess, then like look also at like the timing of things, I suppose, to say like this is essential for this year. It can only be done in this particular year based on some trajectory of some distant exoplanet. And so like that's one of the factors, I suppose.
It is, yeah, it can be a factor. But yeah, it's usually, the scientists are reviewing maybe 20, 30 different proposals. And so, yeah, there might be some that stand out and say, oh, we have to, observe Saturn at this time before its rings disappear, because over time, Saturn, as it's orbiting around, its tilt towards Earth changes. And so we lose sight of the rings. And so that's just one example. I don't actually know if anyone proposed that. I'm just making that up on the spot. But, that is an example of like, oh, it's time critical, potentially, right? Something to do now. And so, yeah, scientists will review these or note like, hey, this is time critical. We really want to do this in the next 6 months, and go from there. But it's really, it's such a challenge because all of the proposal ideas, they have been increasing over time as well. So from the first, we call them cycles of proposals, that happened before launch. We brought in the first round of ideas, and every year we've been getting more and more and more ideas. And so, yeah, now we're up to like 12 or 13 years worth of ideas.
That's so wild. Oh my gosh. And when Webb was launched, I mean, is there at least in the mission, because I know NASA's amazing and always outlive their like mission like lengths that they predict or aim for. What was or what is the mission lifespan, I suppose, that is the goal for Webb, which obviously it's gonna outlive forever. But what was the what's the length of time for it? Is it 12 years?
Well, no, I can start, then Begonia, definitely feel free to add from the engineering side, because I will say, so NASA, I guess, formally has these requirements for prime missions to be 5 years long. So you meet some science requirements within 5 years of operations, but the expectation is you'll most likely last at least 10 years, based on different technical aspects, and that you have enough like fuel to last for 10 years and whatnot. My understanding is we had such a perfect launch and insertion into our final orbit, and journey to our orbit. It took about 30 days to get there, and all that, and everything's been going so well that we could operate for 20 years confidently. That those are the numbers that we talk about on the team. And then but I know the team is tracking anything that might be like what's called a limited lifetime item. Yeah, are there moving parts that could wear out? Is there fuel that could run out? Things like that. So yeah, we definitely have we're expecting enough lifespan, to cover, let's say, these 12 years of ideas that people propose. But the problem is the more we observe with Webb, the more we're learning, and then that creates new ideas on top of existing ideas. So I think we haven't seen the peak yet in the number of ideas. And so I think that'll keep climbing. But yeah, Begonia, if you want to add anything about the lifetime.
No, I think you said it perfectly, right? 5 years was the requirement, which we'll celebrate on the summer of 2027. So we're almost there. Everybody worked to have the goal of the 10 years. And the limiting factor for sure is that fuel. And again, we have over 20 years on that. And yeah, we track those limited life items, but we are hoping we don't see, fingers crossed, I think we'll be there for many years. And what Nicole is saying, I think is because the science is so amazing. When the astronomers take the data, they just realize how much this telescope can do. And I don't see the requests going down. I think it's just going to get harder and harder for the team to select each year the proposals that are more worthy.
Do you think it would be possible to do a servicing mission in the future for Webb?
Well, it's interesting because the fuel was the one thing that, in theory, could be refueled, but is very far away. So at the moment, we don't have that technology. I don't know how things will evolve in 10 years or 15.
I mean, honestly, with the, all the moon projects and everything going on with Artemis and everything, we are hopefully having the capability of being able to get further out easier. I would hope. So it's really fascinating to see like what might happen. Are we maybe it's something that would just become like a commonplace thing in 10 years or 12 years.
Yeah, definitely is there because, we are on that special place, the Lagrange point too, and other telescopes go there. We know the next big one that NASA is going to send, the Nancy Grace Roman, that one in theory is more serviceable than Webb. The instruments on Webb are hidden inside, even if we went there, it would be we couldn't really replace them, but we can refuel it if we understand. And newer telescopes are more, in theory, serviceable, providing we are able to develop the technology to do so. So I agree with you. I think it's something that's there that we'll keep pushing to do, and I think it will come to it eventually, right? Mm-hmm.
Yeah. Oh, that's so interesting. I want to get to some questions. Obviously, I have more questions for you as well, but we do have some great questions coming in that are kind of on this topic too. Two people actually asked this question here. So essentially, if there was a micrometeorite that were to hit, the sun shield somehow, or even the mirror, how could that be compensated for? Or like, would you notice a difference in the images, and what would happen with that? Can you just speak to that topic a little bit?
Yeah, I can for sure. So we know micrometeorites obviously are hitting there. That's one of the reasons on the big sun shield that it has 5 layers. So it's one layer redundant. So we could lose one of them and still keep the temperatures operating. And then also that sun shield is made of smaller sections, right? So if there is a tear because of a micrometeorite, it won't propagate. So, we think we have accounted for that. On the mirrors, yes, the mirrors are seen. I think some of you might remember even during the commissioning period, we get the small micrometeorite hits once in a while. And there was one that was a little bit bigger, but that's one of the reasons the mirrors have this alignment. They are able to compensate for it. And it's something else that happens behind the scenes, at regular intervals, every couple of weeks or even more often. There are measurements that are being made to check if the mirrors remain aligned and to check that micrometeorite impact, and corrections are being done as needed. We don't need a lot of them, but they are definitely. And then we also have an avoidance zone, right? We know where when it's more likely that there is going to be this set of macrometeorites coming, the showers. And the team that schedules the observations for the year that Nicole was talking a little bit about, right? The ones that are located for that year, for that cycle, they are scheduled in the most efficient manner and also trying to avoid those orientations, right? It's a micrometeorite avoidance zone as much as possible. So I think we are doing really well there, and will continue to do so, I hope.
And regarding the sun shield in particular, we just saw that image, for example, there's many layers, as you said. Is it essentially like the Swiss cheese method, where it's like if one kind of like Kevlar, where there's multiple layers, where if it goes through one, it's like it's okay because the other ones will also kind of protect it as well?
Exactly. So there is the 5 layers, so you will have to cross the five of them, and then also the fact that it won't stretch, and you can see there how cool that is. The layer that's looking at the sun is like really hot, and then how cold is the other layer, which is another amazing technology to reduce that heat and give us the passive cooling to be able to do the science without anything else apart from that big beach umbrella.
Is there any concern of the I guess the outermost, the one facing the sun, I guess, that one like wearing down over time with just like the solar winds and everything like that?
Yeah, it could degrade over time, but again, we will be okay with 4 layers. So that we are okay, and that will be, I don't know how long it will be, but we were talking about the life, right? Maybe in 20 years, not only the mechanisms on the instruments, they seem to have a big life, and we are able to have that fuel as well for the small orbit corrections that we have to do about once a month. But we will see, maybe the first thing we will see will be a beginning of a little bit of a degrading in performance. Maybe, if we cannot be as cold or, but we'll just monitor that over the life and work around it as much as we can. Yeah.
Amazing. All right. So another question we have here. What is the process of capturing a close-up of a celestial object? Is it a big zoom lens? Is it longer exposure? How do you actually do that?
Oh, okay. Yeah, I can start with this one. So it all depends, of course, on the type of object. So we have observed images of Saturn, for example. I think I threw one in the deck here, and so Saturn is in our own solar system, so it's relatively close by compared to some of the distant galaxies, of course. And so Saturn is something that when you're looking at an object like this, it kind of fills the whole field of view of the camera. And that's partly because it's so close. And it's each of the instruments, as Begonia was talking about earlier, it does see a different part of the sky, and it has again a different size field of view. So have a wider field of view, some are more narrow. And so with some of these, with Saturn, you don't need a very long exposure at all. It's very close, it's relatively bright compared to other objects. And so it's pretty quick process to capture an image like this, for example. But then something like looking at distant galaxies that you're trying to see towards the early universe, that can take basically something longer in terms of an exposure time, where you're still collecting light for maybe hours there in that case, and you just let the exposure sink in, collect all the photons, and then come up with the image of the full celestial object. But it's all relative. It literally depends how far away from Earth, or from J to T the object is, and it depends too on partly on the brightness of the object as well, whether or not you want the longer exposure. So yeah, there's a couple different factors, which of the 4 instruments you're using, how far away the object is, how bright it is. But astronomers at the Space Telescope Science Institute that I mentioned earlier, they have these calculators essentially that helps observers plan and to optimize their observations, to say, okay, I want to reach this level of signal, this precision in my data. So how long should I expose for to get those photons on the camera here? And so there's processes that we can do beforehand as we're planning out the full observations to really optimize everything.
That's amazing. There's an app for that, basically.
Basically.
That's incredible. And then I guess also just kind of speaking of these images that we're getting too, there's another question here that's kind of related to the spikes on the stars that we were talking about before, Begonia too. So can you touch upon those diffraction of the spikes on the stars? For example, Hubble has 4, Webb has 6. They say, like, is there anything to the number of points on it? Is it have to do with the mirrors?
Yeah, it has to do with the shape of the mirrors. In the case of Webb, there are these hexagonals that we always say that was the most efficient way of putting mirrors together to give us that smooth surface. I mean, we used to say the bees knew it all along, right? We just had to learn that that shape is the best. And then so is how those hexagons are there and the struts that we need to be able to hold them. So yes, it's kind of part of the design of the optics of each telescope, how the mirrors are mounted and how they are held together. And of course, that's known already, right? When the modeling is being done and we already understand the diffraction patterns that will be seen, and all of that is optimized as well on the shape of the mirrors and on the alignment that you're going to do. And again, it varies per telescope. And you can see that I love this image, right? For I know Nicole is exoplanets. When I did research in astrophysics, I did galaxies, and I think this is a beautiful example of this far away, right? Showing us those galaxies that are very far away. And then also the bending of the light, no? That Einstein said, if I have a galaxy that's very far away, but I have something massive in front, I will be able to see that galaxy because the light will bend. And you can see those arcs around it, those kind of arcs. That's the image of a galaxy that's in the background. Probably all the arcs are the same galaxies. So the astronomers that work on that, for me, is another magic piece of astronomy, right? That they're able to understand what's the object behind. They're able to know, oh, all of these ones belong to that same galaxy. And then we know they can work out the mass of what's visible there in the center, and the amount of mass is not sufficient to do the bending of the light that we see. That's one of the clues that we know that there is something there for that dark matter that we don't know what it is, that we can see the effect. So I think astronomy is such a fascinating field, and Webb is giving us so much on anything that you want to know about astronomy.
Can you both talk a little bit more about this bending of the light thing too? Because that is something that I still can't fully wrap my head around. I can like talk about it and kind of understand it, but like I physics was never really my strong suit, and astrophysics, like, oh my gosh. So can you just talk about why it does that and like where it's coming from and how we're looking through like that bend to see other things too? Just imagine I'm like a fourth grader. How would you explain that to me?
Yeah. Do you want me to start and then
Maybe
Yeah,
an eighth grader.
either one. You go, Nicole. Yeah.
Well, yeah, I mean, because you were already talking about, and we can leave this, image up. This is beautiful. And just to go back real quick, this is one that took maybe, I think it was 6 hours of exposure time to collect, in which you see basically anything that doesn't have a diffraction spike, again, is a galaxy. And so, but in the very center, like to the lower right of the giant diffraction spike, that's where you see a lot of those warped features, right? Circling around, the light being bent. And I mean, essentially, there's a lot of mass in the universe. The images like this, they are um, trillions upon trillions of miles in scale. So, it is literally hard for our brains to comprehend some of these sizes. These are astronomical scales for a reason. And so it is hard to also imagine an astronomical mass, right, of these giant galaxies that are many, many billions of times the mass of our sun, essentially. And so when you have something that massive, well, space-time itself is a thing. We talked about space is expanding, the universe is expanding, and it's so space is almost like a blanket, if you will, but it's a 3D blanket. And anyway, when you're having a massive object, it's kind of creating a dip in the blanket, and that can lead to you to bend the light that's around the edge of the dip. So imagine, you put a pillow on your bed and it creates an indent. This is how I think of it. But then around the edges of the indent, some of that light, if it's light on your blanket, this isn't the perfect analogy, but some of that light is getting bent around the edge, because you just have something so massive that's warping space-time essentially. And it is really hard concept to think about, but what is happening, it's you kind of have these massive galaxies in this image, but then there are distant galaxies behind it that their light is getting bent and magnified, and so we're able to see kind of further back in time, because, well, we can tell this a lot of different ways, and maybe Begonia can speak to like spectroscopy side of things too. But there's just a lot of, yeah, it's an astronomical effect. I'll leave it there. Maybe Begonia wants to add more.
Yeah, no, I think I agree with you. It's a difficult concept. I sometimes mention it's like when you have a lens, or maybe it's difficult without the images. Some of these glasses that create these special effects around it because they diffract the light. But I think Nicole was, trying to explain. And there is another one there showing, I think, the furthers, right? I feel with Webb is always a record, right? We'll say this month, Webb has found the furthest galaxy only, 400 million years after the Big Bang. And then a month later, 320,
there's another one.
280, which is exactly what it was designed. And I'm sure, Nicole, I don't know if this is the little red dots. I knew Nicole was going to talk about that. But I think it's finding all these new things that we didn't understand, right? And there were these models about, for example, how galaxies form and evolve over time, but they were based on a few data points, right? And now Webb is giving us this wealth of new data that is forcing those models to be updated, and is showing objects that we didn't know. So it's not that anything is broken, it's just we have new data, right? So now we can expand on this. And I don't know, Nicole, if you were going to talk about these special little red dots.
And I can just add, thinking about I was trying to make an analogy before, maybe it's better to say like a bowling ball in the blanket of space-time, not a pillow.
It's funny you did that. We actually do that at the museum to explain it for group. We've got a piece of like blue jersey basically material, it's a little stretchy, and they all stand around it and hold it out, and then you drop like a billiard ball in the center and it bends the fabric. It bends the fabric. Yes. It's a good visualization of it. I still can't wrap my head around it. But
I mean, it's as if you had an object in front and one behind. If I'm just looking at it and they're perfectly aligned, I won't see the one behind because I'm only looking the one in front. But I'm only looking at this one. But because this one is bending the light, as you both were saying, it's kind of bending. So the light that will normally be straight, it kind of gets bended, so it goes around the edges. It gets distorted, so I don't see it as well. But now I see this kind of ring around it, which is the light from what was behind that. Otherwise, I couldn't see. And again, it's distorted, it's broken down into pieces, but it's giving you the information of something that's behind there, right? So something along those lines. But they are difficult concepts to grasp.
Hard to explain. Yeah, no, I think you both did a wonderful job doing that, though. Like it's the red shift effect. Is that what that's called? Kind of the.
I think that's part of it. I mean, the red shift for sure, which I think Nicole was alluding as well, right?
That gravitational lensing is
this is the lensing, right? Is what a gravitational lensing is like. A lens that's distorting the light. The red shift is another way of knowing what things are far away, right? If we know the composition of an object, we know a typical galaxy has these elements, or a star or a planet, and we know those wavelengths, right? And then because of being far away, they kind of shift, right? And we'll still see that signature, but it's at a different wavelength. And the distance between where we see it to where it will be here on Earth tells you how far it is, right? And that's it moves to the red, and that delta tells you how far away it is, right? Which is where the spectra information is useful, or taking images but putting the filters. If you can move those filters further and further away, it gives you a clue of the light that you're able to see there, right? Anyway.
Yeah. So just to add to that, yeah, you basically I have these cases where galaxies, but sometimes individual stars can essentially just act like a magnifying lens, magnifying glass, and then yeah, you need exactly like Begonia said, that right alignment to be able to magnify the light of something that's immediately behind something else in the universe. And when it gets magnified, it ends up being distorted. These are often called Einstein rings. So Albert Einstein is, one of the most famous scientists maybe ever. And so he came up with this theory, and then we were able to see it with telescopes like Hubble and Webb, which is because they're so powerful, and because even though all of these galaxies, like in this image as well, they're extremely far away. In some cases, I'm not sure of the exact age here, but the little red dots are, sometimes less than 100 million years believed to be created after the Big Bang. So they're very young objects towards the early universe. So that light has taken, billions of years to get to JWST essentially. But even though it's taken a certain amount of time, but the universe is expanding at the same time. And so just like the Doppler effect, the light gets shifted as it's traveling. So it's moving away from us. Everything's moving away from each other in the universe, but it's also really far away. So it kind of gets really stretched out. And so in short, these very distant objects are relatively bright at the wavelengths that JWST can see. And so that is why I think we're able to make so many new discoveries, because this telescope can now see things like these little red dots right here that were not known before, because it was optimized to see some of the very distant light in the early universe. But we didn't realize that there was more to see than what was predicted. I mean, we probably expected to see, discover things, of course, but what exactly we're discovering was remaining to be seen. And I think one of the conclusions of seeing things like these little red dots, it ties back to that astronomers now think that there were more like supermassive black holes in the early universe than originally believed. And so that tells us something about the rate at which stars form and evolve to be able to create a supermassive black hole in the first place. And so it's all tied to like the life cycle and the timeline of evolution in the early universe and how we get to where we are today. So there's a lot of information in just one picture like this.
And this is all really like new stuff too. Like it's just, I mean, I'm sure you guys have been talking about it internally for a while, but we now are just starting to hear about these new discoveries of these little red dots and like, what are they? So, I mean, what are the theories now? If these massive black holes like really existed just a few 100 million years after the Big Bang, what are your all leading ideas for how they formed and so quickly too?
Oh, that's a good question. I don't know that I have a good answer other than that it's raising more questions.
Sure. Science does that, yes.
Yeah, because at some level we make the visual discoveries, let's say, but then we bring in, the people who are theorists to understand like the full evolution based on the real data that we have. So sometimes we have to have a lot of patience in science as we go through discovery. We see something and then we have to, take some time to explain it essentially. But yeah, Begonia, I don't know if you had anything to add for
No, I think I agree. I think the first was, wow, what is this, right? And could it be a very small galaxy that's very red, as you say? Maybe these early black holes, but exactly how did they form, right? So I agree with Nicole that the astronomers that work on that early formation and evolution have to, sharpen their pencils, as we say, and say, okay, your model needs to be changed to be able to explain this. So I think that's how we learn, right? With these unexpected discoveries, which I think we knew. We knew Webb was answering the questions that it was asked for, but it will bring things that we didn't know to ask, right? And I think that has happened with any telescope that we launch, right? There's new things that we learn, and that's how we learn. Yeah.
Are there any other things that Webb has discovered about like the origin of the universe other than these red dots, for example, so far? Like what else have we like learned about that?
Uh, I don't go ahead, Nicola.
Yeah,
What are
no,
you
well, the one thing that, yeah, besides little red dots and um, yeah, the fact that there are more supermassive black holes in the early universe, implying, yeah, that there must have been rapid star formation in at early times. Also, that in general, galaxies, so that are billions of stars put gravitationally bound to each other, that they tend to be. There are a lot more in the early universe, and they're brighter in the early universe than originally expected. And so, again, what does that mean? So essentially, we're finding the early universe is richer than we expected. So,
Yeah.
richer in terms of its composition and everything, and that always has effects downstream because all of these galaxies, black holes, etc., they all contribute, I mentioned, to like the life cycle of the universe. They all have elements that are critical to eventually creating new stars and new galaxies, and eventually planets in all these areas, presumably. But yeah, so there's a lot of early universe, like brighter, richer, active, everything's like we're just finding more in the early universe.
And then I think on any other field of astronomy, they are also finding small new things, right? I think you were saying, Nicole, about maybe a different. They are studying maybe planets that are a little bit smaller than Saturn and Jupiter, and or even on the stars. I mean, we have like a weekly meeting for the operations, and it's super nice that the science side, Nicole and others always bring a 5-10 minute talk of somebody that has taken data with Webb and show us their, this is what I'm finding. And I think it's so wonderful because they are obviously excited about the telescope, but for the operations team, they can see, what's being discovered. And I find every week is a different thing. I mean, you can choose any field of astronomy and there are always new little things, this element we were not sure, or this type of objects we are trying to understand, or so I feel these like glimpses of many things to be learned, right? That this kind of data is now able to do, right? So
You must feel so proud listening to those in the meetings. Like, I did that. I helped you guys do this.
I think it's definitely a team effort. I'm lucky. I have been on Webb 20 years, right? And so lucky to still so excited to be part of it. But it's definitely a team effort. But I think it's a collective happiness. I don't know, Nicole, if you feel the same, but it's kind of a team feeling of, this is wonderful. So, yeah.
Yeah. I mean, I'm just impressed and pleased. Like I said, we're getting so many countless ideas from scientists around the world, and often we're getting ideas from new scientists, people who hadn't proposed to use JWST before. So the community is still growing, and so it's exciting to see that people are interested in Webb, of course, but then also seeing all the great science that comes out of it, and people just pushing the limits of the observatory, stretching to observe really bright things nearby, but then the faintest things far away, and just trying to keep like edging along the boundaries of our knowledge. It's really amazing to see the progress. And again, it's only been 4 years of science, just about.
Wild.
So like, yeah, imagine. And so a lot of that data is also still being analyzed. So it's not even all been published yet. And that's why, we're still just learning kind of from like the first 3 years of science. And there's so much more, that is in progress literally right now. People are at their computers working.
To do.
Absolutely.
Yeah, and we keep adding improvements, right, on the science side. Like we add new modes of observation now that we understand better the instruments and how they are performing. And the scientists say, oh, if we could try to do this, a new way of reading the detectors, and we keep working on that, right? So yeah, it's super exciting.
We have a question here that I'm also curious about here. Of all of the images that you've gathered, do each of you have a personal favorite so far in terms of a discovery of science or observations?
Um, I know it's hard. There's so many. Um, so I included actually, so this is a beautiful nebula, but I believe there's an image of the Carina Nebula. That was one of the first ones to come out. That's actually the one right behind Begonia
Yeah.
as well.
Yeah, yeah.
That one too,
This
yeah.
one, it was one of the first images released, so I think it's fair to say it's become iconic now. And it's on people's desktop wallpaper, iPhone backgrounds, whatever. Um, and I think though this is one of my favorites, kind of because I appreciate when we can come up with ways to describe images like this that are, astronomical in scale, where this is like, I think it's like something around 15, 16 light years wide. So trillions of miles across in this image, but yet this is a like grains of sand, if you can think about it like that, gas and little dust that's being compressed together, gravitationally bound together, that there have stars forming inside of it that will eventually form planets. But we call this also the cosmic cliffs. So it's got, a nice name to it that we can kind of relate to. If you've been to a mountain, the Grand Canyon, any kind of cliff, anywhere, you can kind of make that human connection and think about, even though this whole region is however many times larger than the entire Earth, it still kind of harkens back to something that we're familiar with, a cliff, but in space. And so it gives us that connection again to something that is happening on an astronomical scale. So I just really appreciate that not only is the image beautiful, but it's really informative and just makes us think about the scale and grandeur and connection within the universe. So even though it's one of the first images, it's still one of my favorite.
Yeah, I will agree. That one is beautiful. I was going to say I didn't think about putting them there, but I think the web team does a wonderful job, not only of putting, images regularly that are amazing, but they also do this anniversary image that is always so well chosen. And I remember, I think 2 years ago, it was something called the penguin and the egg, where you can see two galaxies that are interacting with each other. And they do look like a penguin and an egg. One of them was a spiral galaxy, and the other one is that they're being deformed, right? And again, it speaks to how the universe evolves, right? How our galaxy is also going to interact with Andromeda in many millions of years. But I think there are so many that are amazing. Or I'm thinking the Phantom Galaxy that was shown for Halloween, and it has this. So I think everybody can search. They are all amazing to look at, and as Nicole says, with full science. Oh, there you were able to bring it, right? So this will be that's amazing. I think for me it's just to think one of them is probably an elliptical galaxy or doesn't have the arms, and the other one was a galaxy like ours probably, but in this interaction against each other, it's being deformed until eventually they will become something different. And I wanted to mention, just because we know we have the image and Nicole is an expert on exoplanets, right? That the other thing that we're all looking is, a planet that could be, in the habitable zone, right? Close enough, not too far, close enough to the star to have liquid water. And I know it was fascinating for everybody, certainly for me, the system TRAPPIST-1, right, which was discovered a few years ago. It's a star that's redder than our own sun, right? But it has 7 planets, and maybe 4 of them are on this habitable zone where we think water may be present. And Webb is observing each one of those planets, right? And is able to see, one, do they have an atmosphere or not? What does the atmosphere have? How hot it is? And Nicole will probably know more. I know the results from B and C have been released, and they, we knew they would be too hot, not an atmosphere. D and E have been observed. I haven't seen the results, but I think this is another fascinating field where we are like peeling little by little the layers, right, to understand how a solar system like ours could be formed, and eventually a planet like our own, right? And I know it's your field of expertise, Nicole, so I'm going to let you talk about exoplanets and what
about
you're excited about.
The atmospheres, yeah, like how you're able to observe the atmospheres and knowing these sorts of things. Obviously, we know like the Goldilocks zone, possible habitable planets, but can you talk a bit about that with Webb, how you're able to observe those?
Yeah, absolutely. And actually, it's funny because I am part of a program that's observing the planet E in the system. So, yeah. And so, there's a couple different ways we observe exoplanets. So the previous image was just an artist's illustration. So I'll talk about that briefly. But this one, firstly, it's a direct image of a planetary system that's nearby. So there's a literal star symbol there, but there is a real star that exists in the system. It's just that the Webb telescope has the capability to block out the light from the central star. Just like, imagine you're holding up your hand to block out the sun, like it's too bright from your eyes. And so Webb has capabilities to do that. And so when you block out the light from the star, you can reveal the much fainter planets that are around it. And so this is a case where this star named HR 8799 has 4 planets around it. And yeah, all these stars have like telephone numbers, it's fine.
Rolls out.
Yeah, we very, creatively name the planets, B, C, D, E. But this system has 4 planets, and you can see also they're kind of slightly different colors in the image as well. And so there's a couple things we can do with images like this. This is a direct image where we can see, the color of the planet. That can tell us something about its composition and how hot or cold it is. None of these planets are close enough to the star to be of the right temperature to be habitable in any way. And they're also giant planets, think like Jupiter size. So at least 10 plus times the size of Earth. So they're kind of like just gaseous giant planets that are too cold to be hospitable. But this is one way that Webb can study planets and is very powerful. But actually, the main way that Webb studies planets, like TRAPPIST-1, so the previous infographic was showing you, there's these 7 planets around the star, and they all actually orbit very close to the star. And so when that happens, from our point of view, we can observe the star, we measure the brightness of the star, but over time, a planet can pass in front of the star and block some light. And then if the planet has an atmosphere, the atmosphere will block additional light from the star. And so Webb uses this technique, it's called the transit method, to study a lot of different exoplanets. I think it's observed well over 100 different exoplanets now this way. And what we get out is information now shown in this illustration, where you're not taking a direct picture of the planet at all, like in the HR 8799 system, but you're seeing the effect the planet has on the star. And what you see are dips and valleys and peaks and all that. This is a spectrum of light. So imagine just like breaking up sunlight into a rainbow. Imagine like an infrared rainbow. And what we're looking at here is the amount of light blocked by the planet plus its atmosphere as it passes in front of the star. And with Webb, even though we're tens of light years typically from these objects, we can detect signals that are like on the parts per million level changing in the brightness. And so sometimes, and with chemistry, we know like where certain molecules basically will absorb light. And so you can get things like sulfur dioxide, carbon dioxide, water detections, all of that with our JWST. And with our telescope, this is something that previously we could only really have access to water before, but now we can get information on carbon molecules and other molecules that we didn't have before because they all are found in this infrared range. And so the short version for TRAPPIST-1 is that we are using this technique. This is not TRAPPIST-1, this spectrum here. This is like a giant planet. But for TRAPPIST-1 system, all the different planets are being observed by Webb to look for evidence of water and carbon dioxide in their atmosphere. And there have been, I think we have like 19 or 20 observations of the planet E in the TRAPPIST-1 system with Webb already. And so we're trying really hard it's a really small planet. So imagine like it's a really thin atmosphere. So we're looking for a really small dip in or increase in brightness if the atmosphere is there. And so we have to take like 20 observations and stack them to try to build that signal and look for a change. And it's really hard to do because the planets are so small, the atmospheres are so thin. For something like a rocky-sized planet, that's what the TRAPPIST-1 system is. And the other challenge I'll just briefly mention is the stars are also not like our sun oftentimes. And so our star can have like coronal mass ejections and flares and spots and different activity. These planets often orbit stars that are way more active than our sun, unfortunately. So that means that adds a challenge, I'll just say, to the observations. And so sometimes you'll be looking at a data set and you see like this jump in your data, and it's actually like the star emitted a flare, and we can detect that.
Oh.
And so yeah, we have to account for that and hope that that doesn't mean the star is so active that it's eroded the planet atmosphere, because that's also a possibility. So there's a lot of factors at play.
Yeah. I gotta say though, I think that is one of the most fascinating aspects of all of this is the fact that you can use light waves or wavelengths, I guess, to discern chemical compositions of places. That is wild to me, and that's so cool. I mean, and that also, I guess, there's, like you're saying, there's a color spectrum for all of that as well. So, but that, I guess, shouldn't be confused with the pictures that we're getting as well, that originally come in black and white, and then you like ascribe colors to them. Is there any like rhyme or reason why certain of those images get certain color, like the Carina Nebula, for example, like why certain colors are certain ways versus like what we know is actually the light spectrum is this color of an atmosphere? Does that make sense?
Yeah. So I think I'm following. So with something like Carina, or any of the images that show pretty pictures, essentially, even though it's more than pretty pictures, it's
the rainbow colors,
information too. All those images are assigned colors that are obviously colors that our human eye can see. Because imagine you have this infrared rainbow of light, but we can't see the infrared colors. So in the processing phase, there will be assignments made. So maybe like the bluer end of the infrared light will be assigned a bluer color, or the redder end will be assigned a redder color. Sometimes that happens, or sometimes an orange color will be assigned to cover a filter where hydrogen has a lot of absorption or emission. And so the orange is drawing out like all the hydrogen gas or different water features, or so there are reasons that different colors are chosen, but it can depend on the processing. So it's not necessarily the same for every image, I would say. But then when you have the spectrum, there's like the little individual dots that are not a single image. Then that's where most of the information resides, in the spectrum, when you can distinguish like the different chemical signatures, the fingerprints, we say, where water, carbon dioxide, sulfur dioxide, methane, etc. All of those are present. But it's a mix of information for sure, and that's why JWST has well, more than what, 17 different observing modes, ways to study the universe right now. And so oftentimes we are combining all this information to learn as much as we can between images and the spectroscopy.
It's so fascinating. Can you also talk a little bit about, we have a question here. Can you talk a little bit about the process of how stars and galaxies are named? I know we very creatively, you had things like A, B, C, D, E. I mean, is it really just that simple? It's like, oh, this is the year it was found. This is the person who found it. All right. Like, is there any sort of
Oh yeah.
reason
Virginia, do you want to start with maybe?
Well, I know originally the first galaxies, which are the Messier, right? So it was that name and then 1, 2, 3, 4, 5, 6, 7. And I feel for some of the stars as well. Yeah, I don't know, Nicole, if you want to expand. I think it's a little bit, there are so many millions and billions.
I know it is.
And I know on the catalog, right? The catalog that we use for guiding, it has billions of stars, and as Nicole mentioned, they are called like that, HB, blah blah blah, a lot of numbers that way, because it's impossible to think of another way.
Yeah, there's a lot of catalogs out there that were created exactly as Begonia said. Like some of them by ground-based observers, 100 years ago, started this cataloging the different galaxies they could see with their ground-based observatories, or which all the different stars. And so a lot of them have telephone number names. We say, they have the name in the catalog and then a string of numbers. But the brightest stars tend to have more common names because the brightest ones that we could see with the human eye, because those were named centuries ago. And so like Vega as an example, I'm blanking on the names of stars right now. But
yeah, I know.
and like,
and I want to mention as well some of the astronomers that are studying, like well, one of the astronomers that happened, that observes that distant universe, and they have found one of the furthest stars, and they are calling them names from Lord of the Rings. I mean, if they have a particular, like Arendelle, or if they have a particular, part of their science, and they have found that some of them are very creative, and it's a joy. Then you see their papers and they are named. They give them a special name if they're special ones, right? So, and again, I'm blanking out on some of some of the names that even they had given, and but they have been special. So
the
I
naming
think
of it is
if you discover one, I think you can name it.
Name
so
it after
there, everybody should just.
I mean, honestly, namings of things are so interesting. Like, obviously, hurricanes, they kind of cycle through like names, like people's names, or like, I know like there's a dinosaur, for example, that somebody found and they got to name it. And so they named it Draco Rex Hogwartsi, I believe. All of their fandoms in one. Why not? So sure, if they're naming it Lord of the Rings characters, okay. I guess it hasn't been done before. It's unique to that one. So why not?
Exactly. Yeah. Astronomers are very creative.
Oh my gosh, that's great. So I'm curious now, as we're rounding out our time here, but what science are you most excited about that Webb hasn't done yet? Do you all have like ideas of things that you would really like to see now that we've been in action here for, almost 5 years? And, what are you most excited about in the future?
That's a good question. Oh gosh. I mean, it's hard. Well, obviously, like to some degree, you want more in the sense of like, we mentioned earlier, things like little red dots, the things that are newly being discovered with exoplanet atmospheres. We showed, the spectrum with some molecules and all that, but some of the molecules we're seeing we did not expect to see in the atmospheres of the exoplanets. And so that's just driving us to get more data now to confirm the signals or to look for other complementary signals. And so a lot of that is interesting. Like once you see something in one exoplanet, now I'm like, okay, but how many other exoplanets are, is that molecule in now? And because when we understand that as a whole, like what are these atmospheres made of, that really helps us understand the whole evolution life cycle of the atmosphere itself. And we can start to do that for different types of planets, giant planets like the size of Jupiter, or maybe planets that are a bit smaller like Neptune. Neptune's about 4 times the size of Earth, so something, in between Earth and Jupiter. So starting to like take one detection and build on it and see if it's in the population of planets, or was it a one-off, that kind of thing really is what I look forward to seeing. Like, what are the big picture themes, versus some of the one-off discoveries, and what does that mean for how the planets have were formed in the first place and then sustained an atmosphere over time. So yeah, it's just building off all the discoveries that are being made. And I focus on exoplanets, but like little red dots is another good example of that. Like, now people are following up all these, and it's just, I think, scratching the surface.
Yeah, I agree with what Nicole. And then for me as well, right? Understand, I think. And now we all talk about black holes, I remember when I was many years ago, it was like, oh, so exotic. And now we are all like, yeah, our galaxy has a black hole in the center.
They are still very exotic.
So, but to understand how such objects could be formed that early, now that Webb has shown it, and then again, yeah, how those galaxies again, how did that happen? And another thing maybe on the stars is finding these primordial stars, right, that are very massive, and that will be that population 3 that we call, right, that they only have hydrogen and helium. So I feel that Webb has such potential there to help us understand better this formation, and what Nicole mentioned before, even the formation of planets, that is not easy. I mean, the planet has to be there, has to survive the birth of the star with all its events. So I think we have so much to learn. And it's very exciting that Webb is starting to give us all these clues all over, right, for all of it.
And just as we're wrapping up here, Begonia, I would be remiss if I didn't ask you a little bit here. You also were working on the Nancy Grace Roman telescope, right? So
Yes.
Can you just briefly, I suppose, give a bit of an overview of how it's different than Webb and the others? Why do we need this telescope? And just kind of, I don't know, updates on it, right? Like, I know we recently like had some breaking news about it just recently. You were like, oh, I think I can say this now. So tell us more about it. And just for everyone out there who loves this stuff, we are going to try to do an episode on the Nancy Grace Roman telescope too. So don't worry, maybe we'll even have Begonia back again. But can you just give us an overview of that telescope and why we should be excited about it?
Yeah, it's a super exciting telescope. Well, I have to say, the first one named after a woman, so that's special, well-deserving. But as far as the science, it carries 2 main instruments. One of them is a wide field imaging instrument. It can also take a spectra that's able to take an image more than 100 times wider than what Webb and Hubble can do. So that will allow us to get this panoramic view, this big picture, right? All these exciting things that we are seeing with Webb that we have been talking about. Well, how common are they? How common are all these when we look at the bigger picture? And it's going to give us clues on something that we mentioned briefly, right? We know the universe has this dark energy and this dark matter that together form 95% of what's out there. We can see the effects, but we don't know quite what they are. And this is what this telescope is designed to do, give us more information on this. And it will be a great complement to Webb and Hubble, because from that big picture, we can zoom in with the other telescopes. And the other instrument, or the other field that it's going to advance, that we talked about a little bit, has one of those coronagraphs that Nicole mentioned, right? We can cover the light of the star, and we are trying to find those planets, but normally we find planets that are really big, gaseous ones that are far away from the star. We know eventually we want to find something like the Earth. It's a rocky planet, smaller and closer to the star. So Nancy Grace Roman carries a special coronagraph that uses mirrors to, eliminate the light of the star. So we'll be able to see planets a bit closer. So that technology will be very important. And it has other methods that, again, Nicole mentioned, of finding exoplanets with transits and microlensing. We talked a little bit. It also helps us to find planets, as well as that coronagraph. So once Roman is on orbit, we are going to have 100,000. Nicole mentioned we know about 6,000 now. So a big new set of planets to be able to then observe with more detail with Webb. So we are super excited with this telescope. It's going to be where Webb is, so 1 million miles away, and it's on its way to the launch site from Kennedy Center. And we are launching, we can now say, the 30th of August of this year. So very exciting times, and I think we'll all be excited to see it launch and commission and seeing its science come down.
That's amazing. I'm so excited. I mean, Webb is amazing. I got to get new earrings for Nancy Grace Roman now. My goodness.
Yes, it's a great compliment. Webb is still the one that can see further away, but Roman is going to give us that big view, that panoramic view that we need to keep understanding what's out there.
So it's launching at the end of August, and then when do you expect our first images will be coming back from that?
Yes, we will take 3 months to commission it, right? It doesn't have as many deployables as Webb did, but we do have to turn on the instruments, calibrate it, put it on orbit. That will take about 3 months. So the first official images and the operations will start close to that 3-month mark after the launch.
So November, I guess that would be about 3 months afterwards.
Yeah, November. And the data, this telescope, because of that big view, produces like 1.4 terabytes of data. So I think in the first 5 months, it will download as much data as Hubble has taken in its 36 years of operation. But this data is open to the public. Nicole mentioned, on Webb, a lot of it is open. Another one has a little bit of a period. On Roman, most of it is straight away open to everybody in the world, all the astronomers, to start analyzing and finding some answers. And then again, there will be lots of follow-up, I believe, with Webb and Hubble on some of the items that Roman will show. So a very exciting addition to this set of telescopes.
That's amazing. Well, we cannot wait to see that launch. We cannot wait to, I'm sure we'll be streaming it on NSF. I'm sure we can't wait. I can't wait to see all of the pictures and everything that comes back from it as well. And yeah, we're definitely going to do another show specifically on the Nancy Grace Roman Space Telescope, because I feel like there's so much more to talk about. That is just, it blows my mind. Just gravitational lensing in itself. I'm just like, what? But it makes sense. You ladies discussed it very, very clearly here. But there's just so much that people don't even realize. They see the pretty pictures, like, wow, that's amazing, but there's so much work that goes into each of those pictures. So thank you both so much for being here to help to explain all of this stuff, to help catch us up on just the life of Webb, where we've come from to where we are now. This has been really, really amazing. Thank you both so much for being here.
It has been a pleasure. Sure.
Thank you.
Awesome. And yeah, everyone, just a reminder here as we're wrapping up, if you are joining us from the New York City area, first of all, go Knicks, right? Oh my gosh, what an amazing night last night. The city is absolutely wild right now. The collective effervescence, as I say, of the city is incredible. But if you are in the city, you can really feel the excitement, because we are also hosting people from literally all around the world right now for the World Cup as well. So the Intrepid is really excited. We are hosting free viewing parties sponsored by Bank of America for over 50 games out on our pier all the way through the final match. We've rolled out the Astro turf. We've got a bunch of giant screens and food and merchandise and giant inflatable soccer balls. It's a really festive environment. It's a lot of fun, and the vibes are electric out there. What a time to be in the city. So if you are local, come by, visit us. You can visit intrepidmuseum.org for more details, all of the matches and the times. And again, it's all free all the way through the finals. So swing by and cheer on your teams. You can see there on the screen. More ways to find out more. And then also we've got other stuff coming up. We've got our next free movie night coming up on the flight deck on June 26th. We're going to be showing Independence Day at sunset. And then, of course, in celebration of the 250th anniversary of the US, we've also got festive activities on our pier from July 3rd through the 7th. All sorts of partners coming out, military branches doing fun interactives. We've got a tug of war between different military branches as well that we host every year. And of course, also a number of tall ships that will be docked alongside us for Sailforth 250 and the International Naval Review. There's so much going on. I can't even there's talk about naming stars. Like I can barely name all of the things that we have going on at the Intrepid right now. It's quite a summer here in the city. So be sure to come by and visit us, Intrepid Museum. Check out intrepidmuseum.org for more information and join in on all the fun. So again, that about wraps up our show for today. Thank you so much, Begonia and Nicole, for taking the time to hang out with us. Thank all of you for tuning in on whichever channel you are watching us from, the museum social media on Facebook and YouTube and X and the NSF channels and everything. Thank you again to NASA and the New York Space Grant Consortium and anyone else who has sent in their support for the museum's programming as well, so that we can do cool shows just like this. Thank you. If you have actually ideas of things that you'd like us to cover as well in the future, always you could just send us an email and let us know. We are always taking into consideration cool missions and events that are going on. And of course, be sure to join us next month for another episode of Astro Live. We'll be diving into another really exciting topic as always. Check out intrepidmuseum.org to learn more. So everyone, hope you learned a little something today. I know I certainly did, and that you enjoyed the show. But for now, that is a wrap on this one, and we will see you next time. Thank you so much for watching.
And here we go.
There's the deluge. Here's ignition.
Doubling up.
Did it just do a curveball?
Back to the moon and beyond.
Put that in the big bag,
Back at home, we all have a lot of work to do, but from here, Earth sure looks like a perfect world.
Propulsion continues to be normal.
We did have an observation. 343 unfolds to go.
It's orange.
Water towers can fly!
Bingo! Right in the center. Where's Jacqueline? There it is!
That was surreal.
That's not what we want to see.
No!
Oh my God.
Yikes. You bet. We don't need any more of these.